Good day everyone. So we are still here on our topic boundary layer, and let's now move on to the boundary layer in external flows condition. Okay, so actually it is a divided in two subtopics of boundary layer. We have the velocity boundary layer, and we have the temperature boundary layer. Okay, like what I have said last time, that the concept of this boundary layer includes the up to the temperature boundary layer. Okay, so let's have first a simple illustration of this concept. Let's say we have x and y axis here, and since we are in internal flows condition, say we have a let's take a simple case of fluid flowing over a flat surface. Sorry. Okay, so say this is our flat surface, and to start with, say we have a fluid stream initially on this left side with some velocity, right? So initially, before the fluid goes with contact with this flat surface, we can see that it has a velocity profile that looks like this. Okay, so a fluid stream on this side at some velocity, say let's call it at some velocity u infinity. Okay, so the moment the fluid stream makes contact here, as it flows through this flat plate, okay, the fluid layer at the interface comes into zero velocity of the what we call no slip condition. Okay, as it flows through this layer, through this position, the moment the fluid comes in contact with this flat surface, then the fluid layer, this layer that is in contact with the surface, comes into zero velocity. So in contact, zero velocity here, velocity of the what we call no slip condition. That is letter D, condition. Okay. So as the fluid goes along this goes along in this solid surface, it is seen that the profile will look like this. So the one that is in contact is at zero velocity, I mean we have a no slip condition, and the profile of other layer will looks like this, right? Up to this velocity. Okay, so from 0 up to this velocity. So that is the velocity profile of this is the velocity profile of this external flows using the concept of the boundary layer. Okay. This fluid layer then, when in contact, or when it moves along and contact with this surface, the fluid layer acts to retard the motion of the particles in adjoining fluid layer. That's why it created this kind of layer. Okay, this acts to retard the motion of the next layer, and then to the next layer it retarded the motion of the next layer, and so on until such time that it reaches the distance distance sigma from the surface. So this distance here from the surface is the distance called the boundary layer thickness. And if we take a look at this using this free stream, we can view this as something like this. Okay, so this is okay. So this is actually your free stream. Okay, so from here your stream will look like this. Okay, and it created a boundary layer that looks like this. Okay, so at this point it retarded the motion of your fluid until at the distance sigma from the surface. Okay, until sigma from here to this point. Okay. And then from here to here up to the top of your fluid, then you can now have this kind of velocity profile. Okay, the quantity sigma is typically defined as the value of y for which u is equal to 0.99 u infinity. Okay, so this one. Okay, as this boundary layer changes as our x increases. Okay, so the region below the boundary layer, this boundary layer, where the friction of the fluid is significant and affecting this velocity profile, then above the boundary layer is the region where the friction is negligible. So above this above this boundary layer, the friction between this is negligible. That's why it has this profile. Okay, so the formation of boundary layer is because of because of some momentum transport and the retention of momentum displayed by the fluid mechanics parameters, like what we have said last time, like the dynamic viscosity, the density, what else, and so on. So it is the, it is the relative ability of the fluid to change its momentum, right? So actually the density is the relative ability of the fluid to maintain its momentum, okay? And the ratio of the two is called the, what we call the kinematic viscosity V, okay? We have already encountered this term, the kinematic viscosity, and actually the kinematic viscosity, it decides how far the presence of the plate will be felt by our fluid stream in terms of the velocity gradient, okay? If our kinematic viscosity is large, then we can expect a higher or greater boundary layer thickness. Okay, so that is the relationship of those properties.